All right, guys, we're finally able to talk about calculus now. It's one of my favorite things to study about math, and I'm hoping I can share some of that with you. First of all, what is calculus? Calculus is the study of continuous change. So you might be thinking, well, why would I need this in real life? Why are we doing all these complicated, crazy mathematical acrobatics to study change? Well, it turns out there's a lot of applications in real life. So I'm not talking about, how fast something is happening. I'm asking how fast is something changing. So for example, let's say later on in years, when you're old enough, you go to a bar and you order a beer. This beer is sitting out on the counter. The bartender is giving you this beer. Well, you're wondering, how long after it has been taken out of the fridge will this beer be too warm to drink, for example? Or you can think about, a population is changing. Let's say you're growing bacteria because you're a lab scientist, go crazy, and you're wondering, hey, how fast is this population changing? Is it growing fast enough? Is it dying down fast enough? Or you're working with chemicals and you're wondering, hey, let's say there's this harmful chemical, but it's dissipating, or it's a drug in the body and it's slowly decreasing. How fast is it decreasing? Is it decreasing fast enough at the rate that we want? So that's all study of calculus. It's continuous change and how fast these changes are happening, okay? So before we can talk about, these applications, we need some background information. And this is about something called the slope of a tangent line. We know what a slope of a line is, right? Your line, y equals mx plus b, great. There's a slope, rise over run, done. But what is a tangent line? So we're not just going to be limited to straight lines like this, because that's not a lot of fun. Instead, we have a lot of crazy graphs, crazy models out there. This graph underneath is one of them. It looks a little bit more complicated than just a straight line. A tangent line to a curve at a point is a line that most resembles the curve near that point. What does this mean? I'm going to use this diagram to help us out. Pretend that this is a mountain, okay? And you're this teeny little person walking up the mountain. Okay, great. You're walking up, you're walking up, you're walking up. As you're walking up, you notice that, there's a change in how steep the mountain is, right? How steep the surface is. The steeper it is, the harder it is for you to climb up. At any given point, so let's say you're at this point right here. It's almost as if you're going up a straight wall, a straight line. So if I draw a line that touches this point exactly at this point, but no other point near this point, so it just kind of touches and then goes away from the line. This is what we call a tangent line. Notice that this line looks nothing like the entire curve. It looks nothing like the whole mountain, but when you're really close to this point, this line resembles this part of the mountain the most. Okay, that's what a tangent line is. Okay, now the slope of the tangent line is really cool. It actually tells us how quickly the curve is changing at that point. So if you're this little guy over here and you're like, how hard is it to climb up the next section of the mountain? Well, look at the slope of the tangent line. The steeper the slope is, the steeper positive slope is, the harder it is for you to go up. The smaller the slope is, the easier. But then when it comes to the negative side, so let's say you're on this side of the mountain now, you want this to be a big negative number, so it's kind of fun. You can even roll down the hill, okay? So in this case, you want the slope to be a negative, all right? So that's the whole idea behind tangent lines. It turns out that if we have the math behind all the calculus, we could really easily calculate the slope of any tangent lines. But without it, which is the stage we're at right now, it's really hard for us to just eyeball on a graph how to draw on this tangent line, what is the slope going to be. So before we can talk about how to construct a tangent line, we have to go back a step and talk about something called a secant line. So when you're given a graph like this, and you're given 2 points P and Q on the graph, the secant line, or the secant, between 2 points, P and Q, is a straight line that connects these points. So this dotted line here is called a secant line. It's a straight line, so straight lines have slopes. The slope of the secant line is going to be rise over run. So remember, whenever you read a graph, you always read it left to right, just like reading a book. So rise means I need to figure out how did I go from my initial y value, y1, to my final y value, y2. So that's y2 minus y1. And then my run is going to be how did I get from my initial x1 value to my final x2 value. So that is x2 minus x1. So what we're going to do to go from a secant to a tangent is I'm going to take this point Q and move it closer to P. So as I move it closer to P, notice what happens. I start to get a line that looks more and more like my tangent. So as I get closer and closer and closer to P, so at some point I'm going to get a Q like this, when I draw the secant between these two, look at what happens. It's pretty much the tangent line. I know, pardon my poor drawing, but it's pretty much just the tangent line as you get closer and closer to P, right? So what I'm going to do is I have this point P that has the coordinates A and B. So x is A, y is B. My Q, I'm going to move it so close that it's essentially A plus H is my x coordinate. Okay, so it's just H distance away from my x coordinate. Then what's my y coordinate going to be? Well, my y is just going to be the y at A plus H, or f at A plus H, right? Instead of subbing in x in my function, I'm subbing in A plus H in my function. So let's see what happens to my slope. The new slope, which is still rise over run, my rise is going to be the difference in my y values. So that's going to be f at A plus H minus f at A. Okay, so this is the y value for Q, this is the y value for P, divided by the x value for Q, which is my A plus H, minus the x value for P, which is A. So again, x value of Q, x value of P. And if I simplify this, I'm going to see that my slope is essentially f at A plus H minus f at A divided by H, because A's cancel. That is the slope of the secant line as the secant line gets closer and closer to the tangent line. So now we have a way to find the slope of the tangent line, and I want you to write this down. The slope of the tangent line to a curve at a point P is the slope of the secant line between the point P and a point that is arbitrarily close to P. Arbitrarily close means that I can make it super close. So 1 unit is not close enough. Half a unit is not close enough. 0.1 of a unit is not close enough. 0.00001 of a unit is not close enough. It can get closer and closer and closer and closer to P, where it's practically the same point as P. To illustrate this idea of arbitrarily close, we have to introduce this new concept called limit. Don't worry, we're going to talk about a limit a lot more in future sections. Okay, I'll explain very clearly what it is. But right now, what we need to know, and what I want you to write down in this box, is that the slope of a tangent line to a curve at the point x equals A equals the limit, we write it as LIM for limit, as H approaches 0, meaning this distance between this point that's sliding closer and closer to P is practically 0, of f of A plus H minus f of A divided by H. Okay? To evaluate this limit, we're going to talk about this way more in future sections, but for this section, when we evaluate this limit, we want to simplify the expression enough so that when we substitute H approaches 0 into the expression, we get something that makes sense, meaning we get a number or we get some kind of infinity, something that we can actually understand. Okay, let's take a look at this example to help consolidate our idea about secant lines and tangent lines. So given this curve here, y equals x squared plus 1. So essentially, this is a parabola shifted up 1 unit, so something that looks like this. This is our curve. We want to find, in part A, the slope of the secant line between 2 points. So remember, in general, slope is just rise over run, so that's your y2 minus y1 over your x2 minus x1. Okay? So in part A, we know that x1 is 0, x2 is 1, so our slope is going to be y2, which is the y value corresponding to x equals 1, so that's f of 1, minus y1, which is the value corresponding to x equals 0, divided by x2 minus x1. Okay, f of 1, we're subbing in 1 into this expression. we get 1 squared plus 1 minus f of 0, do the same thing, 0 squared plus 1, divided by 1 minus 0. And if we continue to simplify this, we're going to get 1 over 1, which is 1. Okay, let's continue on. This time, I want to find the slope of the secant between x equals 0, so that's my x1, and x equals 0.5, which is my x2. So the slope now is going to be f of 0.5 minus f of 0 divided by 0.5 minus 0. So let's crunch this up. This is going to give us 0.5 squared plus 1 minus 0 squared plus 1 divided by 0.5 minus 0. And notice that the 1's will cancel. We're left with 0.5 squared divided by 0.5, which is 0.5. I'm going to pause the video at this point. I want you to go ahead and finish C, D, and E. Find the slopes of the secant lines between x equals 0 and the point x equals 0.1, x equals 0.01, x equals 0.001. If you need to use a calculator, go ahead. I don't want you to stress over that. So hopefully you were able to come up with these numbers. I know they're really small decimals. You could use a calculator or use some algebra to simplify them. In part C, the slope you get should be 0.1. Then in part D, 0.01, and then part E, 0.001. So the numbers are getting smaller and smaller. You can see this trend here, right? Let's actually talk about what this is before we move on to part F. I have this secant line first between the points 1 and 0 like this. So I get some kind of secant line like that. And then what I'm doing is I'm getting closer and closer to 0. So my next secant line is going to be between 0 and 0.5. So x is 0.5 would be somewhere there. And then I'm drawing a secant line. And my next one is going to be between 0 and 0.1. So that's something like this. I'm drawing this secant line. And then the next one, you get the picture. It gets closer and closer till it almost looks like the tangent line at the point x equals 0. Okay? And what's happening to the slope of these secant lines? They're decreasing. They're getting closer and closer and closer to 0, right? So in part F, using this knowledge, if we wanted to estimate the slope of the tangent line at the point x equals 0, well, since the secant lines, the slopes are getting closer to 0, and the secant line is getting closer and closer to the tangent line, I know that in part F, the slope of the tangent line is going to be approximately 0. Okay? It's going to approach 0. It might as well just be the slope equals 0 for the tangent line.